All right, hi everyone. Welcome back to AOS, Multiprocessor OS Part 2. I'm still Ihor, so I'm here for the rest of today. And then you'll get Gernot back, I believe. So this is a Part 2 of a two-part lecture. Last time on Tuesday, we talked about kind of a background of what multiprocessor OSs are. So what's the idea of multiprocessor OS? How is it in principle supposed to work? And then what is the main issue behind kind of building and running a multiprocessor OS? And that issue is scalability. So we talked about kind of what does scalability mean in a multiprocessor system, and we looked at Amdahl's law, and we kind of found out that the more serial sections you have in your code that can't be parallelized, the slower your system is going to run, and the less it's going to scale. And so one of the core things with designing and building a multiprocessor OS is to try to avoid the serialization so that it scales well. Then before going to look at actually how we design and build multiprocessor OSs, we looked at multiprocessor hardware. So we looked at a bunch of issues or kind of factors of multiprocessor hardware. We looked at kind of the structure of it. What does it look like? How many cores does it have? Where are the cores located? We looked at things like memory locality. Where's the memory located relative to the cores and stuff? We looked at cache architecture. What does the cache architecture look like? We looked at interconnects. What do the interconnects look like? What's the bandwidth and latency between processors like, and stuff like that. And then today we're going to look at actually how to design for multiprocessors. So I put up a little summary slide of what kind of the conclusions from Tuesday, from the other day. Basically, in terms of scalability, we see that multiprocessors are growing. So we're getting, commodity systems of 50+ cores, experimental systems of hundreds of plus cores. And at this scale, this is where Amdahl's law really kicks in. So you really get scalability problems if you have even a little bit of serialization. And so it's really important to be aware of that and be aware of how to avoid serialization. We get heterogeneity as well. So not only we get heterogeneity of cores, we get different kinds of cores that are all on the system together. We have different kinds of memories that are all on the system together, and so on. We also have heterogeneity of things like interconnects. So the connection between two pairs of cores may be very different. So you need to know kind of what your system looks like to understand what the interconnects are and how that works. We also find that because of this heterogeneity, properties of otherwise similar systems may be very different. So you may take two AMD platforms, but because of the different interconnects, because of the different ways they're set up and so on, they may actually have very different properties. And so running multiprocessor software on that may have different consequences for different design decisions. We also found out that most modern multi-core systems are NUMA machines, so that's non-uniform memory access, where the memory is not always equidistant to all the cores. So some cores may be closer to some memory and other cores may be closer to other memory. And so the latency to get to different memories is going to be different. We looked at cache architecture and cache coherence, and we found that it gets complicated to keep the caches coherent, particularly with the different interconnect structures, with the scale of the systems, the number of caches that there are, the different kinds of caches. It gets really complicated, and so a large chunk of the hardware real estate is used for logic that actually manages the caches and manages cache coherency. And in some systems, they just don't implement cache coherency. So you get systems like the SCC, mostly experimental systems, where they forego the cache coherency to add more cores, for example. So in some systems, we don't have the caches, and so we can't rely on kind of using shared memory for communication, but also for synchronization and so on, and so or for locking for that matter. And so in some cases we may have to do it ourselves. We may have to have some kind of explicit communication, explicit synchronization for shared data structures. And then all of that kind of combines to show us that the computer nowadays is more of a distributed system inside than it used to be. And so we can consider that as a bunch of nodes that are connected by a network that don't necessarily share anything. And so in order to program distributed systems, we need to be able to do message passing. So explicitly send messages between the various nodes. We need to worry about things like consistency and synchronization. So if we have copies of memory in different places, we need to make sure that those copies are consistent if we change anything. And we need to synchronize those changes. And we start needing to worry about fault tolerance. So what happens if there's a bug in our routing protocol? What happens if one of the cores stops working? Does the whole system go down or not? It's not really that common that cores stop working as it is in distributed systems, but we start seeing more and more kind of faults that we need to deal with in multi-core systems that are similar to distributed systems. So that's kind of a summary of what we talked about last time. And then we're going to move on from that and build on top of that. And so really focus on OS design for multiprocessors. One of the things we talked about last time was this need for scalability. And so we want to optimize our systems and our code for scalability. So what does that mean? Well, how do we do this? First, what we can do is we can reduce the amount of code in critical sections. So make sure our critical sections are small. That'll increase concurrency. That'll reduce the serialization, right? Because critical sections are inherently serial. You can only have one running at a time. So we want to reduce the amount of code in that. That leads to doing fine-grained locking. So there's this kind of idea that you want to lock data, not code. So rather than, for example, in your kernel, having a big kernel lock, a lock that locks all of the kernel code, you want to have locks that protect the various shared data structures only. And so you only need to lock when you access a shared data structure rather than whenever you run kernel code or whenever you run a part of the kernel. So you really want to focus on this idea of locking data, not code. But there's a trade-off there, right? The more concurrency, so with fine-grained locking, you get more concurrency, but the problem is that the locking implementation itself also causes serialization. And so you've got this trade-off of potentially your lock implementation is going to cause you more problems than the benefits you gain from having that fine-grained locking. And so you need to weigh off those trade-offs and find the right granularity of locking. The other option is to use lock-free data structures. So data structures where concurrent processes can access those data structures, read and modify them without necessarily having to do locking. So that allows you to reduce kind of the amount and effect of the code in the critical sections, so to reduce the serialization. The next thing you can do is try to avoid expensive memory accesses. So these are things like try to avoid accessing uncached memory. Take advantage of the cache as much as possible. So set your memory up, set your data structures up such that they're likely to be in cache when you need them. And access cheap memory. So in a NUMA machine, you want to access the memory that's close by rather than the memory that's far away. So you want to set up your systems, your software so that it does that. Then you want to do things like reduce false sharing. So make sure you pad your data structures so that independent data structures don't share a cache line, for example, right? So that if one core is accessing one data structure and one core is accessing a different data structure, you don't start getting problems with cache conflicts and so on. Then you also want to reduce cache line bouncing, so reduce the sharing in general. So for example, implementations of MCS locks use local data. So you want to reduce the amount of shared data even in your implementation of locks, but in implementations of shared data structures and so on as well, or reduce the need for the shared data structures. And then you want to reduce the number of cache misses as well. So things like affinity scheduling, which means you want to run processes on the same processor and close to the memory that they're accessing. Right? So if you're running a process on a particular processor, it's going to fill its cache up with the memory, the data that it uses. And then if you reschedule it on a different processor, it won't have all that data in the cache. And so it'll spend and waste a lot of time getting that data into cache. You want to avoid that. And so you want to have control over where you're scheduling your processes so that it's close to the data that it's already collected, but also close to the data that it uses. And you want to avoid cache pollution. So basically, you don't want to evict the data that's in cache if you can help it. In particular, if you're switching to run the OS from an application, you don't want to just get rid of all the application code and fill the cache up with OS code, because then when you switch back to the application, it's going to have to get all that data back in. And likewise, when the app runs, you don't want to evict all the OS data structures from cache, because otherwise the next time you go into the OS, it'll waste time loading its cache up there as well. So these are all things you want to do in order to write software that's scalable, and that includes your operating system. And so based on kind of these kind of optimizations, some design guidelines for building OSs and software for modern multiprocessors are avoid shared data, right? So interestingly enough, a lot of the performance issues arise less from the lock contention, so actually contending for locks, but more based on data locality, right? So the cost of actually getting that shared data can override the cost of the locking itself. While avoiding shared data, you want to have as much explicit communication as possible. So you want to regain control over communication costs and the predictability of communication. In particular, when you're relying on shared data for your communication, you're relying on the cache coherency implementations for a lot of your communication. And a lot of that is, A, expensive because it gets really complicated to keep those caches coherent, but also opaque in that you don't actually have an overview, you don't have a good insight into how that's necessarily implemented in your hardware. And so you're relying on this expensive but potentially opaque mechanism for your communication. And that's a problem because then it's harder to optimize for that. Whereas if you have explicit communication, you have an explicit communication mechanism that you know how much it costs, but you also know when you use it. If you're relying on kind of shared memory and cache coherence, you don't necessarily know when that's going to result in communication over the bus, right? When the cache coherency is actually going to kick in. And so you're kind of guessing a lot of times. But if you have explicit communication, you have more control over what's going on. And having control means you can optimize things, you can understand where serialization is and try to remove that. Sometimes it's the only option. So if you look at architectures like SCC and so on that don't have a coherent cache, then you really need to do explicit communication. You can't rely on the hardware implementing something for you. There's a trade-off you have to make between parallelism and synchronization. So as we've seen, synchronization, like doing locking and stuff like that, introduces serialization, right? Causes your system to stall essentially and not be parallel. So you want to have as much kind of concurrency as possible, right? Try to make your threads, your concurrent threads, as independent as possible. So reduce the number of critical sections, reduce the possibility of cache misses and stuff like that. What you're aiming for is what they call embarrassingly parallel, right? Embarrassingly parallel programs are programs that can essentially run completely independently parallel. So if you think back to the previous lecture where I had these examples of a program with a bunch of parallel code and some serial code, the embarrassingly parallel program is the one that only has the parallel code. And so they can be run completely in parallel. They don't need to do any communication. There's no serial sections and so on. So you'd want as much of your system as possible to be like this embarrassingly parallel. That's not always possible because you will need to do some kind of communication, but try to make it as much as possible like that. It's important to allocate for locality. So if you're allocating memory for a process, then make sure that memory is being allocated from memory that's close to the core. So your system needs to be aware of where all the memory is located, where it can allocate from, and how that's going to be essentially allocated. Like if you're doing a memory alloc or something like that, where is that memory coming from? So you need to understand where the local memory is and allocate for locality. And likewise, you need to schedule for locality. So we talked about this before, but you want to schedule processes with their cache data. So you need to know where they've run before, where their cache data is likely to be, and schedule them there, as well as with local memory. So if you have a process that has allocated a bunch of memory in a particular kind of NUMA area, then when you reschedule it, you need to schedule it on a core that's close to that memory. So you need to understand A, what's close to that memory, B, what memory it actually has and where it's located, and then use that knowledge when you're scheduling. And then one of the difficulties is that there is a trade-off between uniprocessor and multiprocessor performance and scalability. So all of the things we do in order to make scalable software, like having critical, having locks, doing synchronization, extra work for allocating for locality, extra work for scheduling for locality and stuff like that, is all extra code, right? So A, that adds complexity, but B, that also affects performance. And so if you're going to be running OS software or any software that's optimized for running on a multiprocessor system on a single core, then you're going to be doing a whole bunch of work for nothing. And so you need to understand that doing all this scalability stuff does have a cost to it. And so it doesn't make sense to do it if you're not going to actually be running on a scalable machine. But you also need to know what your target is, right? Are you targeting something that's 4 to 8 cores, or are you targeting something that's 20 cores, or something that's 100 cores? Depending on what you're targeting, you want to do more or less of these kind of things as well. So these guidelines are nice, right? It's nice to have these guidelines in the back of your head, but how do you actually build something that adheres to these guidelines? How do you build a system that will be a good multiprocessor system? So there have been a bunch of people that have thought about this and looked at it and thought of ways to do that, and have come, there are basically what comes out of that are a bunch of different kinds of design approaches to building these kind of multiprocessor OSs that ensure that a bunch of these guidelines are met. And so for the rest of the lecture, what I'm going to do is go through these various approaches and show examples of kind of research systems that have introduced these ideas and how they work, and some of these examples. So I'll give you a summary of the approaches and then dive into those approaches themselves. So the first one is divide and conquer. And the idea here is that we take the multiprocessor and we just divide it into a bunch of smaller processors or multiprocessors. So we treat a system, if it's got like 10 cores or something, we might treat it as 2 5-core systems. Something like that, right? Or a bunch of like 5 2-core systems. And then use them kind of as normal. Then we don't have to make that many changes to our software. So options for divide and conquer are use virtualization, so run a bunch of virtual machines, or use something like an exokernel. So an exokernel is like a really small kernel, and all it does is manage the hardware. It basically provides you with hardware abstractions. And we'll look at a couple of examples of how exokernels can be used to provide this kind of divide and conquer approach. The other design approach is to reduce sharing. So to build your system, but keep in mind that you want to reduce sharing as much as possible. And so either take an existing system and go through it and just find out everywhere where the things are being shared and think about how can we reduce that sharing, how can we make that more performant, how can we reduce the impact of that sharing. Or you can start kind of from scratch and say, okay, I'm going to design a system, and from scratch I'm going to design it so that we reduce sharing as much as possible. So we'll look at those two approaches, kind of the take an existing system and reduce the sharing in it, or build a system from scratch that reduces the sharing, or gives you mechanisms to reduce the sharing. The other approach is to just do away with sharing and build a system that inherently doesn't share anything by default. And if you want to share something, then you have to do extra work to actually do that sharing. So this is where we really treat the computer as a distributed system. And then the last thing I add there is we also need to consider the heterogeneity. So I mentioned this last time, that systems are becoming more and more heterogeneous. We've got these systems on the chips that have a whole bunch of different processors, a whole bunch of different memories, and so on. We need to deal with those. This is also going to be part of building a multi-core operating system in the future, is dealing with all of these various different kind of subsystems and processors. So we'll talk about how to do that, or some approaches for that as well. Okay, so we start with divide and conquer, and the first example is a system called Disco. So Just a meta comment first before I go into that. I'm going to present a whole bunch of different systems that basically give you design approaches for how to do multi-core processor operating systems. And the format I'm going to have is there's going to be kind of a system name. There's going to be often kind of some kind of slogan, some kind of really short description of the approach. And then I'll give you some context, like when was this started? What did the world look like when people were looking into this project, when these projects were developed? And then give you an overview of what the idea is behind it. And then in subsequent slides, I might go into some more detail and provide you a little bit more detail about the systems. So first system is Disco, and kind of the slogan here is scalability is too hard. Right? It's too hard to write a scalable operating system, so let's not write a scalable operating system. And the context was around 1995. Large CC NUMA, so that means cache coherent NUMA machines, were starting to appear. And people were having to go from their nice kind of uniprocessor machines to these large CC NUMA machines and write operating system software for it. But scaling existing operating system software to these large machines requires a lot of modifications, and it's a lot of work. And so the idea behind Disco was, is there an easier way to do that? Is there an easier way than taking Unix and going through the code and changing everything and making it multiprocessor aware? Can we just take our existing Unixes and run them on the multiprocessors without having to modify them? And the idea behind Disco was to implement a scalable virtual machine monitor. So to use virtualization and then run multiple OS instances on this single machine on separate machines. So you have this virtual machine monitor that takes the multiprocessor and represents it as a bunch of separate smaller machines. And then you can take your off-the-shelf OS and software and just run it on these various machines. So you don't have to modify your OSs, but you're taking advantage of your multiprocessor hardware. And kind of the key concept was that, well, a VMM really has most of the features of a scalable OS, right? So you need to create a VMM that has a NUMA-aware allocator, so that if you're setting up the VM, you set it up to be NUMA-aware. It does things like page replication, remapping, and stuff like that. It does really the core kind of OS stuff. And if you're implementing just that, not a whole Unix OS, then it's easier to implement that in a scalable way. Modern incarnations of this, like we see this a lot now in the cloud, right? So you've got Amazon and so on. They have virtual servers. So you'll have, they'll have big machines, and then you'll be able to rent, like a 1-core or 2-core or a 4-core machine on that, right? And so you have virtual machines running on that, and others will be running virtual machines on the same computer and so on. So this idea, is alive and well currently, and people are using that. So to give you an idea of the Disco architecture, I've explained this, but the picture is kind of clearer, I think. What you have is you start with your CC NUMA machine. So we've got the PEs, or processing elements. So these are your CPUs. They've got an interconnect. They're connected together, and they're connected to memory and so on. And then on top of that, we have Disco, the VMM, running on top of that. And it splits the machine up into separate, smaller machines. And so you can have, a single processor machine with your OS and some applications running. You can have a multiprocessor machine with an SMP OS running, some parallel jobs on top of that. Again, you can have some more single OS machines running, single processor machines running. And you can even have a multiprocessor OS processor machine running with a dedicated custom OS, for example. So this thin OS is an OS that's developed in order to specifically run parallel scientific applications. So it's not a full-blown Unix OS, it's just a custom dedicated OS for running a specific scientific application. And so that can run on some processors. And you can run all of these at the same time. And they can often talk to each other. So you can have your SMP OS that's running parallel make to build some software, contacting the OS that's running the NFS server that has access to storage, right? And that's where it's getting its files from to do the build and so on. And so you can create these kind of clusters on a single machine, essentially. I think the next slide. No, this slide. So one of the big things that came out of this disco work was actually a revival of virtualization work. So decades before, there was virtualization work done on mainframes and so on. So the initial kind of virtual machines and so on came about with that. And that kind of died down, and this revived it. In fact, the people that did this went on to found VMware and really kind of found the renaissance of virtual machines, and that led to the virtualization in the cloud and stuff like that. And now we can't do anything without virtual machines anymore, basically. So this kind of led to the renaissance of that. So performance-wise, the whole point of this is to take advantage of the multiprocessor OS and get some scalability, get things to run better for free, right? Or cheaper, at least, than having to rewrite a multiprocessor OS. So what they did was they did some benchmarks, some experiments, and what they did was they ran a PMake, which is a parallel make, so basically building in parallel. And they ran it on IRIX, which is a version of Unix. And this kind of bar represents IRIX running on, I think it was an 8-core machine. Yeah. So IRIX as an SMP OS running on an 8-core machine. And this is kind of the execution time. And the higher the execution time, the worse. The lower the execution time, the better, because there's a particular make build that you want to do, and you want to see how fast you can do that. So this is normalized to 100. So the SMP OS is at 100, whatever 100 means. And then what they did was they took a disco VM where it was just one VM on the same machine, so basically an 8-core VM, and then ran IRIX on that. So basically exactly the same thing, but with virtualization overhead, and so you can see it takes longer. So the virtualization does provide some overhead. And then what they did was then they had 2 VMs, 4 VMs, and 8 VMs. So this is 2 4-core VMs, this is 4 2-core VMs, and this is 8 1-core VM. And then basically ran the PMake over those machines and saw how long it takes. And so as you can see, basically the smaller the machines, the better. The faster it takes, because there's no synchronization anymore, right? When you've got the bigger machine, the bigger kind of machines, there's still some internal synchronization going on. And as you get less and less. Then there's an experiment here where they kind of compare running Splash, which is a benchmark suite, high performance computing benchmark suite, on IRIX, so the SMP IRIX, and then on a dedicated operating system for that benchmark suite. And this is running on, I think, a single VM both times, right? Because it's the same cost. And so you can see that having like a dedicated OS for your application can help a lot. It's much faster to do that. The takeaway message here is kind of, yes, you can do this virtualization, but really the best thing is just have single core machines doing your parallel work. PMake is quite embarrassingly parallel as well, which is why you get that result as well. If you reduce the serialization to almost nothing, you get the best results. Okay, so the next approach I want to talk about is this idea of space-time partitioning of your machine, and the project there is Tesselation. So they introduced this term of space-time partitioning, and essentially it's kind of 2-level scheduling. So the context is it's around 2009. There's a lot of highly parallel multi-core systems around, and this is at the Berkeley Par Lab, and their goal is to figure out how can we make the most of this, up and coming kind of multi-core systems. We're going to get to many core systems. How do we re-architect and rebuild our software systems so that they take advantage of that? And that's for everything from, they look at hardware, they look at OS software, system software, they look at application software and stuff. And the idea was to kind of have a vision, have some kind of result for how to build our software systems in the parallel world. So the idea with tessellation and space-time partitioning is that you create partitions of resources. So if you have an application running, it's going to need some set of resources to run. And resources in this case are processing and memory, network, storage, interconnect between the processors and stuff, so bandwidth, things like that. And so your application would be able to say, okay, I need 2 cores, I need 2 gigabytes of memory, I'll need access to the network, and I'll need an access to the disk, for example. And then another application might say, well, I need 4 cores, I need 16 gigabytes of memory, I don't need any network, I don't need any disk, for example, and so on. And so what you do is Tesselation allows applications to specify what kind of resources they need. And these, we call these spatial resources, right? These are like hard resources that you need. And then the other thing it does is the time part of partitioning is that it schedules applications to run by kind of fitting the resource requirements together. So applications can run in parallel as long as their resource requirements don't overlap. So if you've got, let's say, an 8-core machine, and you've got one application that requires 4 cores, another application that requires 2 cores, and one application that requires 3 cores, then you could potentially schedule the 4-core and the 2-core at the same time, or the 4-core and the 3-core at the same time, or the 3-core and the 2-core at the same time. But you can't schedule all of them at the same time. And the idea then is that you have these kind of partitions of spatial resources, and then you schedule them all together. Right? It wouldn't make sense to, for example, if you have an application that requires 5 cores and another application that requires 5 cores, to schedule 3 of the 5 cores and 4 of the other 5 cores at the same time. Because then they're not going to run very well optimally. They're going to be missing some of the resources that they require, and then when you reschedule them, there's going to be conflicts and so on. So you really want to schedule everything together that the application needs and make sure that they're scheduled well together. So that's the idea of this space-time partitioning, is that applications partition the resources that they need, and then you schedule those resources as those partitions, so they get the most of everything. So there's kind of an example picture. We've got kind of our hardware. We've got the Tesselation OS, again, which is a very kind of minimal OS. It's like basically like an exokernel type OS. And then on top of that, you run your applications as well as any of your operating system code on top of that, and you schedule it accordingly. So kind of a different view of Tesselation here is, again, we've got kind of the hardware partitioning mechanisms, which is your hardware. And it depends what your hardware provides, how well you can do that partitioning, right? So typically, partitioning CPUs is pretty straightforward. Partitioning memory is pretty straightforward. Partitioning interconnect is maybe harder. You might not be able to reserve a particular bandwidth for a particular application. Partitioning cache may be harder. But you've got whatever mechanisms the hardware provides, and then you've got this kind of Tesselation kernel, which has 2 levels. It's the partition mechanism level, which is responsible for programming kind of the hardware and making sure that it's partitioned accordingly. And then you've got the management level, which is doing all of the shuffling, basically figuring out, okay, what are the resources, what are the partitions we have, how can we schedule them accordingly, how can we kind of tessellate essentially all of these partitions together in time. And then on the top, you actually have your applications, and they implement application functionality, but also library OS functionality. So the idea, again, this is kind of an exokernel type approach where your kernel is really minimal. It really provides only a hardware abstraction. And then your application has to provide all of the OS functionality, normal OS functionality, as well as the application. And typically the approach to do that is to take a library of the OS functionality, link it in with your application, and just run it as a single process. Right? And you can have a bunch of those running, and they can have very different OS personalities then. So that's the Tesselation approach, this idea of space-time partitioning. Yep?
How does the Tesselation approach interact with applications who either can't have an accurate prediction of the resources they'll need, or how many resources they need changes a lot over their lifetime?
So typically, what it has is an interface that allows you to request more resources or change kind of the resources that you need. So your partition can change over time. So an application can start and it can say, well, I just need 1 core. And then as it runs, it could, for whatever reason, decided that it needs more cores. And so it changes its resource requirements. It tells the kernel. And the kernel keeps track of that. And then in scheduling, it needs to keep track of these partitions and their current requirements. So you see here, there's kind of resource queries and requests going down. And you've got kind of partition resizing and so on. So yeah, it does deal with that dynamically.
So there's 3 different compute types.
Okay, so the next design approach category that we're going to talk about is reducing sharing. So we've looked at divide and conquer, how to take a multiprocessor machine and kind of split it up into separate machines. Now we're going to look at how do we build or modify systems to reduce the amount of sharing in that to make them more scalable. So the first system we're going to look at is called K42, and this is a research operating system. Context 1997 to 2006 is when it was being developed, and as an operating system for these CC NUMA machines, so these cache coherent NUMA systems. It was developed at IBM and University of Toronto, and was kind of successor to some other projects from there, Tornado, Hurricane, and so on. And the idea was to build a full Linux compatible operating system using a whole bunch of interesting research ideas. So the goals were high locality, so make sure that when you're accessing memory, it's local memory, you're reducing sharing that way, and high scalability, so make sure that it can scale to large multiprocessor machines. Some of the main techniques that they introduced were object orientation, this idea of building the operating system out of fine-grained objects. We'll talk about that. Clustered objects or distributed objects, which improve data locality, make sure you access local non-shared data, and this idea of deferred deletion, so essentially avoiding locking, and this became later RCU, read copy update, which was adopted by most systems as one type of lock-free data structure. And then also NUMA-aware memory allocation, since this was for CC NUMA machines, they were looking at memory locality and making sure things were allocated according to locality. So the first thing I'm going to talk about is the fine-grained objects in K42. So it was an object-oriented system, so everything was implemented as objects. So if you're designing a file system, for example, you'd have file descriptors as objects, you'd have files represented as objects, you'd have blocks represented as objects, and so on. And the idea was to make that fine-grained rather than coarse-grained. So here's an example to illustrate that. If you have coarse-grained objects, so for example, there's an object that represents the virtual file system, and that inside itself contains, a table of file descriptors and things like that, then there's going to be a lot of sharing when a bunch of processes try to access this virtual file system, right? Because every time someone wants to allocate a file descriptor, it's going to need to go into the shared data structure and make sure to allocate the right one and so on. Likewise, if other objects are also coarse-grained, there's going to be a lot of sharing when they're accessed. So the idea with K42 was we'll make all of those objects as fine-grained as possible. So rather than having a big VFS object that contains all the file descriptors, make all the file descriptors their own objects. And so when you want to access a file, rather than accessing this big object, you're accessing this little object. And they're less likely to be shared because different processes are going to be accessing different files. So when you are actually using different files, you're accessing different objects, and so you're avoiding sharing that way. So having these fine-grained objects avoids a lot of unnecessary sharing, which is the general idea behind using fine-grained objects. So that helps a lot. The other thing is sometimes there are objects that are shared. So for example, if two processes are going to be accessing the same file, they're probably going to be accessing the same object, and so there's going to be some sharing, especially if they're on different cores, these processes. So the idea is, well, let's try to reduce the sharing involved in accessing shared objects. And this is where they came up with clustered objects. And the idea is that for an object, you have a globally valid reference to that object, so every object has a reference, but when you dereference that reference, you get a reference to a local version of that object. So every core would have a local representative of this global object. And when you invoke operations on that object, you would act on local state as much as possible. So an example, this picture is an example of a shared counter. And so a shared counter is essentially a counter, right? 1, 2, 3, 4, 5, 6, 7. It keeps a track of the value of the counter, and it has 3 operations. It has an increment operation, a decrement operation, and a get value operation. And so this kind of outer circle represents the global shared counter, but when each process accesses that counter, it gets its own local copy of it, a local representative of it. And then the counter is implemented in such a way that when you do the most common operations, so for example, increment or decrement, then it only acts on its local version. So when you do an increment, it only increments your local representative's value. And so what happens is all the values obviously become out of sync. So if process 0 does an increment, and process 1 does a decrement, and process 2 does an increment again, and if they all started at 0, for example, then process 0 would have a value of 1, process 1 would have a value of -1, and process 2 would have a value of 1. So they'd be all out of sync. But then the get value operation would require communication between all of them. So as soon as someone did a get value on the counter, then they would all have to synchronize and get the right value. So it'd be like 1 + 1 - 1 is 1. So the ultimate value would be 1. Everyone's local copy would be updated to 1, and then you could call that. And the idea then is to optimize for the common case. Right? If everyone's constantly incrementing or decrementing and very rarely getting the value, then that would work really well, because none of those increment or decrement operations would actually cause any communication or any sharing. And only when someone tries to read it would they actually do that. So that's the idea behind that. The cool thing about doing it this way is there's a lot of transparency. So for example, if increment, decrement are the common cases, then you implement it that way. But if the common case suddenly changes, then you can change the implementation of it to make, for example, get value the common case, do local reading and increment, decrement to cause communication without affecting the processes that use it, because they still have the same interface. They still see it as an object and they're invoking functions on that object, but now the way it works might change if the use case changes. So that's really cool. It gives you transparency. It makes it less complex, but it gives you a lot of control, and it gives you that locality. And yeah, so they kind of introduce this idea of the fast path, right? Like kind of accessing mostly local structures. So when you have a fast path in your system, then you want to make sure that the structures that you're accessing are local, and so you want to optimize your or distributed clustered objects to be local on that fast path, for example. So that helps a lot as well. And then they took K42 and they did some experiments to show how well these things work. The nice thing was that because K42 was compatible, the API was compatible with Linux, they could compare it to Linux. And so what they did was they took a bunch of programs, systems, and set them up, one on Linux, one on K42 with just these shared objects, and then one on K42 with distributed objects. So they had kind of the benefits of fine-grained objects and then the benefits of fine-grained plus distributed objects. And so what we end up seeing is for this experiment, as we scale up with a number of processors, we see Linux kind of doing pretty well and then starting to do unwell. Whereas when we look at K42, we look at it with the shared objects, it kind of doesn't do as well as Linux, but it does scale a bit better than Linux. So eventually, it'll have better performance than Linux. But if we add this distributed objects, right, these localized objects, then we see it does really well and it scales really well because it's mostly avoiding sharing. And that's one of the things that causes a lot of serialization. So a different approach is represented by Corey. So this is a system. The context here is, this is around 2008. We're starting to get high-end multi-core servers. So people are starting to get interested in kind of, oh, we're going to end up in this many core world, right? We're going towards, we've got 50 cores, we're going to go towards hundreds of cores and so on. So we really need to tackle this problem. The goals of Cori, this is at MIT, the goals for Cori are to look at how can an application control the OS sharing. Because the idea is that, well, the application knows how much sharing it might need to do. Is it going to run just a single process on a single core, in which case the OS shouldn't share anything for it? Is it going to run a bunch of processes on different cores that are going to need to share? Perhaps the OS needs to do more sharing. So the idea here is the application needs to control how the OS is sharing its data structures. So this was kind of a from scratch experimental OS. Again, it's exokernel-like, so it's very minimal and only provides very basic hardware abstractions, and everything else needs to be implemented as a library OS and an application on top of that. By default, the OS would only provide single core abstractions or single core access to the OS data structures. So any data structures that would be allocated would by default be single core. And then if the application wanted the OS to share more, so for example, it knew it was going to run on a bunch of cores and it would need key data structures to be shared, then it would need to call into this exokernel and say, this range of data or this data structure will need to be shared amongst these cores. And then Cori would do that. So it kind of flips things around from by default share everything to by default don't share and explicitly ask things to be shared. So it had basically three kind of key abstractions that it provided. This was the idea of address ranges, so a chunk of memory that you could either be available to a single core or to several cores. The idea of cores itself, so you could manipulate kind of how many cores are available for an application. And then shares, so how are things shared? How are data objects shared? And so you could control all of those. So that was interesting. That was an interesting approach to things. Of course, it was an experimental OS, but the idea was kind of give more control to the application who knows how much sharing is going to be needed. Then, a couple of years later, the same person actually did this work on Linux brute force scalability. So again, this is 2010. Again, we've got high-end multi-core servers. This is at MIT as well, the same person that did Cori. And the goals are to look at how to scale a commodity operating system. So take Linux and do as much work as you can to make it run well on a 48-core machine. So that was the goal. Kind of an interesting aside is this kind of inverts the way a lot of research is done. In that typically what people do is they'll take Linux and try to fix Linux and get frustrated at not being able to, and then go off and build their own system, right? And this guy did the opposite. He built his own system first and then went and fixed Linux. So that's kind of interesting. They got some really good results. So the kind of the grayish box is regular Linux, and the green box is with all the changes they've made on a 48-core machine, I believe. And they created a benchmark suite for multi-core systems and so on. And as you can see, in most cases, their patches and stuff make quite a significant difference. In some cases, it doesn't. So what did they do? They basically applied previous lessons learned, previous work done on parallel computing and multiprocessor operating systems. So they did things like apply sloppy counters, and sloppy counters are essentially that distributed counter I showed you with K42, where you're basically doing all the work locally and synchronizing only when you need to. As much as possible per core data structures, so make sure that the data structures are allocated and used per core rather than shared. A lot of fine-grained locking, a lot of lock-free algorithms. Keep track of cache lines, so make sure there's no false sharing and things like that. Ultimately, 3,000 lines of code were changed. So a little idea of kind of which changes affected which benchmarks. You can see the GMake benchmark didn't get affected by any of the changes, and as you can see from the performance, they were the same. Yeah, the conclusion of this was there's no real scalability reason to give up on traditional operating system design. So this guy, tried a different OS design, went back to Linux, and figured out that if you do enough work, Linux can scale pretty well. The kind of sad thing was that, at least when this work was done initially at the conference where this was presented, someone asked, has this been upstreamed to Linux? And the answer was no, it's too hard. So this person went and sweated and made all of these changes to make Linux scale, but the actual process of upstreaming the changes to Linux were too hard, and so they didn't do those. I'm sure some people took a lot of that work, and other people did it as well, but it's kind of unfortunate. So, same group again, a couple of years later, is thinking more about scalability, right? They've got a bunch of experience with other multi-core projects at MIT, right? They've done Core, they've done this Linux scalability, they've done MOSBench, which is their multi-core benchmark, and so on. They start asking themselves, well, how do we know if our system is, really scalable now? Have we done everything we can to make it scalable? And so typically the way things are done is you've got this workload-based evaluation. So you have a workload like MOSBench, for example. You run it, you look at the results, you figure out what doesn't scale, you find the problems, and you fix them, and then you run it again and see that it improves, which is good, but there's two questions that come up is our benchmark suite, the workload, complete, right? Are there any workloads that we've missed that might have scalability problems? And then the other is, have we found all the bottlenecks in the code, right? Are there other potential parts of the code that we've missed? And so you kind of never sure, you can never sleep well at night. You're never 100% sure that you fixed everything. And so they ask themselves, is there something fundamental that makes a system scalable? Is there something we could look at, kind of over the whole system and be able to point at and say, well, this makes it scalable, it should be scalable, but it's not. Or these things won't be scalable, so we don't have to worry about them. And so they decided, let's look at the interface, right? The API of the system, of the operating system. And the interface itself might be a bottleneck. It might not be possible to implement kind of a scalable version of a particular interface. And so what they came up with was this thing called the scalable commutativity rule. And the rule is that whenever interface operations commute, they can be implemented in a way that scales. And so what does it mean that operations are commutative? What does it mean that they commute? It means that you can't distinguish the order of operations from the results. So if you have operation A and B, then based on the results of running A and then running B, you can't tell which one was run first. So you can't tell whether A was run first and then B, or B was run first and then A. And if the API has that property, then those operations are commutative, because you can run them in any order and you'll still get the same results. So a negative example of that is create in Unix says that the result of create will be the lowest available file descriptor will be returned. Now this isn't commutative, because if you run A then B, A will get the lowest file descriptor and B will get the next lowest file descriptor. Whereas if you run B and then B will get the lowest file descriptor and A will get the next lowest file descriptor. And so you can tell by the results in which order they were run. And so they're not commutative. That's an example kind of explaining commutativity. And so what they're saying is if you have commutative operations, then they can be implemented in a way that scales. And why is that? Well, if the results are independent of the order, then it should be possible to implement them without requiring any communication between them. And that should be implemented in a scalable way. Essentially, they don't need any shared data. They don't need any communication, so they should be embarrassingly parallel. So if you have an API that is commutative, it should be possible to implement that in a scalable way. And so this is a really nice result because it can inform your software design. When you're designing an API that's meant to be scalable, then you know what to aim for. You know to aim for operations that are commutative, and so then they can scale. But when you're implementing, you also have a clear target, right? If you're implementing something that's commutative, then your target is something that doesn't do any sharing, that scales. And the nice thing also is that it allows you to do workload-independent testing. So if you go back, think back a couple of slides, one of the problems they had was, are the workloads that we're using to test scalability sufficient? Well, now they don't need to have workloads. And the workloads were things like running Memcached, running SQL servers and stuff like that. Now they don't need to have those kind of workloads to test whether something's actually scalable or not. And so the way they do the testing is they have a symbolic model of their API, and then they have a program that analyzes that and determines any commutativity conditions, so whether the APIs are commutative or not, and then generates test cases that test any of the edge cases that might require sharing, might be commutative. And then runs those tests on QEMU, on a simulator, and looks at the cache usage. And so it'll run these operations in parallel concurrently and look at the cache usage and see if there are any conflicting cache lines or not. Because if there are, that means there's some sharing going on. And then it can look and say, well, these operations are commutative, they shouldn't have any sharing. But if they do, you know there's problems, and that's where you can look at fixing things. If there isn't any sharing, then don't worry, don't bother with that stuff. And so they ran this on Linux, and they saw that, yeah, there's a whole bunch of implementations where they should be commutative, they should be scalable, but there is sharing going on. And then they implemented their own kind of teaching operating system based on this rule, and then tested that out and found that, yeah, most of the things that were commutative, they could implement them without having any of this communication, any of these conflicts going on. And so that's a really cool result, and it's a really nice result because it's not a specific result like let's hack Linux as much as possible to make it scale, but it's a general result that can inform people's development and design, which is really important. So another project that, again, looked at how to reduce sharing, how to reduce conflicts, was FlexSC. The context, again, around 2010, there was a lot of work around 2010 on multi-core operating system because these commodity multi-cores were coming out, and everyone was worried about, well, what if our old software is not going to be able to scale? We need to look at this problem. So that was a really popular problem. Again, University of Toronto, the same kind of group, the same university where K42 work was done and so on. And their goal was to look at and reduce the context switch overhead of systems. So when you're running your user level code, you switch context into the kernel, run kernel code, and then switch back to the user code. We know that context switches have some overhead, right? There's some kind of machine overhead involved in doing the context switch. But what they found that was really interesting was there was a whole bunch more overhead related to caches and evicting of data out of caches when you switch the OS. So if you look at this graph, the x-axis is instructions per cycle, so how many instructions are being executed per cycle, and then the y-axis is just time, and you see kind of the system executing. So you've got user level kind of executing, you've got about 1.5 instructions per cycle, and then it switches into the kernel. And the IPC number tanks to like really low, and then slowly kind of goes back up. After it, so this graph basically only shows the IPC at user level, right? And so there's the point where it goes into the kernel, and then the next point is when it's back in user level again. And you can see user level runs really slowly and then slowly speeds up again. And the reason for that is when it switches into the kernel and the kernel runs, a whole bunch of cache is evicted, right? Because the kernel evicts a bunch of the user data in the various caches, right? In the I cache, in the D cache, in the L caches as well, but also in the TLB. right, which is essentially cache for the page table. And then when the user code starts running again, it takes a long time to kind of get that back in to the cache. And all of that time is just stalled, which is why you have a very low instructions per cycle count, because the processor is just waiting, doing nothing. So that's really interesting. So they figured, okay, well, there's this cache and TLB pollution. What can we do about that? How can we fix that? And so their approach was this idea of asynchronous system calls. So the idea is when you do a system call, you invoke a system call, rather than that context switching into the kernel and doing a bunch of kernel work, it writes the system call information into kind of a system call page, and then doesn't go into the kernel, but just continues executing user code. And then the next system call writes some more stuff into the system call pages, and then after a while switches into the kernel, and the kernel does all these as a batch. All the system calls get executed as a batch, and then the results are written back there, then goes back to user level, and then they can read the results and continue executing. And the idea there is that you don't have that constant kind of cache pollution. You just do it once for a whole bunch of system calls and back. And so you amortize the cost of that context switch. And then the other thing you can do also is, rather than wait for a while and switch to kernel mode, you can just have dedicated processors to running the kernel code. And so the processor running the user code never switches to kernel code, to kernel mode, and so doesn't suffer that. Yeah.
So, but like, maybe I missed something, but like batching the system calls means the processes that invoke those don't immediately get their responses back?
Yeah. Yeah.
So is there like a trade-off there? Like,
there is a trade-off
between the batching and the delay between the cost of
yes.
TLB and
yeah.
pollution?
Yeah. So there's a trade-off there. And if you're the only one running and you're not doing any asynchronous system calls, then that's not a good idea, right? Because you're going to wait. But that's the next part, this flex threads, is typically there's a lot of threads running on a system. And so what you do is you overlay a bunch of these threads on top of the system call mechanism. And so you run a bit of one thread when it does a system call, you go and run a bit of another thread until it does a system call, you run another thread until it does a system call, and then you do the system call and come back up. So it's going to be a bit more delay for every thread, but you're kind of amortizing that over running more threads at once. So it has to be the right kind of workload to benefit from that. But it's a really good observation. So they also did a bunch of experiments. In this case, they're running Apache with FlexSC batching as well as system call core redirect. So on one core where there's no core redirect, it's all running on one core. The green line is throughput is on the x-axis, so the higher the better. The green line is regular Linux, and the gray line is FlexSC. So you see just the batching itself gives you a benefit. Again, this is Apache getting a whole bunch of web requests as a benchmark. So there you can really benefit from that kind of batching of threads, for example, right? That kind of a whole bunch of threads. You've got a lot of work. What I'm trying to say is you've got a lot of work that you need to do, and so you don't really suffer too much from those delays. And you can see that it performs significantly better. The more cores you have, the better the performance gets. So as you get more cores, you get essentially more parallelism. And you reduce the serialization by running it on a separate core, for example. So that helps reduce the sharing as well. So we've looked at a whole bunch of mechanisms for how to reduce sharing in systems, from doing brute force work to having the scalable commutativity rule to trying to batch stuff, avoid the cost of kind of jumping into the kernel and stuff like that. And the amount of sharing in a system is kind of a spectrum where on the one hand you have kind of a lot of shared state, you've got a big kernel lock and stuff like that. And as you kind of move down, you've got finer grained locking, you get kind of clustered objects and partitioning, you've got all these approaches to remove sharing. But at the very other end of the spectrum, you essentially have no sharing. And so the idea Now, so this is a different design approach category of NoSharing. The idea is rather than starting at the left end of the spectrum and reducing sharing, let's start at the opposite end of the spectrum with no sharing and slowly add sharing if it's really necessary. Right? But we start with kind of a distributed system. We've got distributed state, and we can create replicas and add sharing if it's necessary. But by default, we start with no sharing at all, and then slowly we start adding sharing. So an example of this is Barrelfish. Again, the context is 2007, 2010. Again, these large multi-core machines are starting to appear. We've got the threat of hundreds of cores coming up. We've got NUMA CC and non-CC NUMA machines. And so this is work done in Switzerland, ETH Zurich, and some collaboration with Microsoft as well. And the goal, again, is to look at, okay, how do we make a system, an operating system that can scale to many cores, to hundreds of cores? And another thing they looked at, and we'll talk a little bit about that later, is how to support and manage heterogeneous hardware. Right? Not only are we getting more cores, but we're starting to get heterogeneous cores as well. How do we deal with that in the same operating system? And so their approach is to structure the OS as a distributed system. Really think of it as a distributed system, and one of the key defining aspects of a distributed system is that you don't have shared memory. Right? So you start off with the idea of there's no shared memory. All communication is explicit. So anytime you want to communicate between cores, you need to be sending messages between cores. You don't write to some memory and magically the hardware will make the memory appear somewhere else at a different core and have this implicit communication. No, you have to do explicit communication. The OS structure has to be hardware neutral, and any state that has to be shared rather than being shared is replicated, explicitly replicated, and you need to do explicit work to keep that consistent. It doesn't happen magically. Barrelfish is a microkernel-based operating system. It's similar to SEO4. In fact, it's based initially on the SEO4 specification, so it's a capability-based OS, familiar to most of us. And so the general structure of Barrelfish is that you've got your multi-core machine, so you've got a bunch of CPUs, and then each CPU has what they call a CPU driver and what we generally call a kernel. So this is the microkernel kernel running in kernel space, the CPU drive. And so each processor has an independent kernel running on it. So there's no kind of shared memory between any of the kernels. They're completely independent. And then on top of that, you've got user space. And Barrelfish introduces a special user space process called the monitor on each processor. And the monitor is able to kind of dig into the kernel and do things like create capabilities and so on, manipulate capabilities that other processes aren't allowed to do. So it has some special access to the kernel. And then any synchronization of state between the kernels happens through the monitor. So state that needs to be synchronized between kernels are things like capability lists. Right? So C spaces need to be synchronized. The kinds of capabilities need to be synchronized. There needs to be synchronization when capabilities are retyped, for example. When untypes are retyped, everyone needs to know that. And so their lists need to be synchronized. That actually happens at user space by the monitors. So whenever anyone wants to retype something, for example, the monitor will get that call. It'll communicate explicitly with all the other monitors to do a synchronization protocol. And then all of those other monitors will go into their kernels and modify the data accordingly so that they remain consistent with each other. But all of this state is replicated rather than shared. So the kernels don't have any shared state. And then on top of the monitor and the kernel, you have applications. And you use the usual kind of SEL4 style capabilities of having untyped caps and frame caps and page table caps and mapping things and so on. And so it's up to your applications whether they have run on a single core, whether they run on multiple cores with shared memory between them, whether they run on multiple cores without shared memory and so on. It's up to the applications to do that. The monitor and the CPU driver make sure that the kernel data is always and the hardware as necessary is always appropriately synchronized. But it's always done explicitly at user level with message passing. So replication is important here in Barrelfish. Again, no shared data structures, but any data structures that would traditionally be shared are replicated and kept consistent explicitly. So I think I've mentioned most of this. The monitor does that. We've got things like memory allocation tables, address space mappings, capability lists that are replicated, that need to be kept consistent. And then the consistency and coordination are done at user level. So we use two-phase commit for retyping. So if the retype's done, then the monitors implement a two-phase commit protocol to do that. Things like page mapping and unmapping, the TLBs need to be synchronized so that all the TLBs should be synchronized so that everyone knows where memory is mapped. Whenever anything's mapped or unmapped, then there's a one-phase commit, basically sending a message out to everyone saying, shoot down the TLBs or resync your TLBs. Interesting thing with Barrelfish is how the communication is done. So on most commodity multiprocessors, cores, there's no real explicit communication mechanism. So if you think back, if you remember the SSC, the single chip cloud computer, they actually had an explicit communication mechanism with these message buffers. But most contemporary commodity multi-core systems don't have explicit communication mechanisms. So the communication on those is through interprocessor interrupts. So you can essentially cause an interrupt to fire on another processor, or through shared memory and caches. It turns out that IPI's, interprocessor interrupts, are slow, so they needed a different way of doing communication, this message passing in Barrelfish. So what they did was, intra-core, if you're on the same core, you just use your regular kernel endpoints and do your communication. But if you're communicating between cores, they have this thing called user-mode RPC. And the idea with that is to abuse the cache coherence that the processor implements to do your message passing. So what they would do is they create this shared buffer. So you have a shared buffer with anyone who wants to communicate with anyone else. So they allocate memory, and it's the same physical memory. Or it's not the same physical memory, but they share cache lines. And the sender then writes into a cache line. So if you want to send a message, you choose a slot in the buffer and you start writing into it. And the receiver will sit there polling on a cache line, waiting to receive a message. And then once the sender is finished writing into that cache line, the cache coherency mechanism kicks in and takes that data and copies it to the other core, and then the receiver can start reading it. And so in that way, they kind of abuse the cache coherency to implement message passing. So there's some optimizations there. For example, the receiver polls on the last word of the expected message so that the data only gets transferred once the message has actually been finished writing. And then we've kind of learned that polling is a bad thing because you're just wasting cycles reading on a particular word the whole time. The interesting thing here is that the polling is only really expensive when you're reading something that causes the cache to actually be migrated across. And that only happens when the message is ready to be sent. Otherwise, that poll is really cheap. So if you're expecting a message and you're polling on this, it's not really doing anything. But nevertheless, if it's going to take a long time, then you're best off to stop the polling and switch over to like a interprocessor interrupt mechanism and wait for that to happen. So kind of several levels. Like if it's coming quickly, you poll, and if it's not, you stop and do something else. But this is a really neat kind of mechanism of how to do explicit message passing even though your hardware doesn't provide you with those primitives. Okay, so if we look at some results from Barrelfish, some performance results, this is comparing the cost of this explicit message passing versus the implicit cache coherence of accessing memory. And so what we have is a very simple benchmark where there is a program, and all it does, the goal of the program is to write a particular number of cache lines as fast as it can and see how long it takes to do that a certain number of times. we've got different options here. So the blue ones are using shared memory. So there's a server and a bunch of clients, and they all map the same memory. They're all writing to the same memory, and they're just trying to write to that memory as fast as possible. And all the clients need to write a certain number of times to that memory. And so SHM1 is just 1 cache line, 2 cache lines, 4 cache lines, 8 cache lines. And then we do this on 2 cores, on 4 cores, on 6, 8, 10, and so on. And then the red ones are using Barrelfish message passing. So the red ones, we have a server process and client processes. So there's one that does 1 cache line of writes and one that does 8 cache line of writes. But these are sending messages. So the clients send messages to the server, and the server writes to that memory as fast as it can, as fast as it receives the messages. And so we see these results where relying on shared memory, especially if you're writing a lot of data, just gets slower. And so latency is on the x-axis, so high is bad and low is good. You just see it gets slower and slower and slower because there's, in this case, there's like 16 clients all trying to write to the same memory, and it's the cache coherence delay that's causing them to be really slow. The less data you write, the faster it is. And then you see here with the explicit message passing that there is some delay, and it gets slower and slower, but not nearly as fast as it does when you're doing shared memory. And so this is sending a whole bunch of messages to the server. The server is really fast because it's writing to local memory that's not shared. And so those writes are really fast. It has no cache coherence delay or anything like that. So that's going really fast. And this is the delay of sending the message and getting a reply back. And so you can see this scales much better than just using shared memory. The interesting thing as well is the delay for the shared memory is actually the processor being stalled. The processor can't do anything else while it's waiting, whereas this delay is actually just blocking. And so you can schedule and do something else with the processor during this delay, whereas with the blue lines you can't. And so this shows like the power, or actually kind of the slowness of shared memory when you've got a lot of cores, but also the power of this message passing. Some other experiments. So they implemented a multicast using this message passing. So essentially sending a message to, well, there's unicast sending a message to every receiver. A multicast is sending a message in a tree shape to a receiver, and that one sends to some other receivers, and they send to other receivers. And then they also have a NUMA-aware multicast where those groups are actually NUMA-aware. So they compare that to using kind of just a broadcast, which is a shared memory operation of writing to everyone, and show that explicitly doing communication and being able to explicitly control communication by creating these multicast trees can be much, much faster. And so having this control over your communication can really improve your performance and your scalability. There's kind of a little bit more practical result with using TLB shootdowns and comparing Windows and Linux. So TLB shootdown is if your page table mappings have changed, then you need to kind of flush the TLB on all the other cores. So you need to tell all the other cores that your TLB is invalid. You need to shoot it down and you need to reload it because the mapping has changed and you don't want other cores to use stale mappings. And so Windows and Linux implement this using interprocessor interrupts. So if a TLB shootdown needs to be done, they'll send an IPI to all the other cores, and they will then flush their TLBs. Whereas Barrelfish implements it using this multicast that they implement with the message passing. And this experiment basically shows, again, latency, high is worse, low is better. On the number of cores, that Barrelfish can get a much better performance on this interprocessor communication than using IPIs. Okay, so that kind of covers Barrelfish, which is, yeah.
Just a quick question, just curious. Is there a reason that both Barrelfish and Linux have a very large standard deviation on some specific number of cores? Or is that just a statistical anomaly?
I couldn't tell you that.
Okay, that's it. I just
So yeah, so that essentially is kind of the no-sharing approach. And Barrelfish did this. There were some other systems that did this as well. There was MIT, I think, had Factored OS, which was a similar kind of approach to this. The last thing I want to talk about is heterogeneity. So how to deal with, or some of the issues and how to deal with those issues of heterogeneity. So if you remember back to 2 days ago, I talked about heterogeneity of modern systems, in particular modern system on a chips, SoCs. They have a lot more processors than we typically think of. Right? So the top left is our application processors, and this is what we normally model as our multi-core systems. Right? So all the other examples of systems were basically in that top left corner. This was, your multiprocessor systems with NUMA and so on, and with the interconnects and so on. But actually, in a modern system, there's a whole bunch of other processors all over the place, right? There's some kind of real-time processors that you can do. Well, this is doing boot power management and clustering and stuff like that. There's a real-time processor for some peripherals. There's the GPU. There's security processor and so on. So there's all these various different processors. And they also have access to the system resources, right? So they have access to system memory, for example. But we typically only concentrate on the OS in the top left corner. And that programs the MMU, and we figure, well, those are the only processes that can access memory, so we're safe from that. There are I/O MMUs, so system MMUs that protect peripherals from accessing or control how peripherals access memory as well, that are meant to kind of protect your main memory from those other things. But it kind of becomes a big mess, and there's different code running on it. That code may be proprietary, it might not be proprietary, and so on, running on it. And it leads to a bit of a problem. So this is going to talk about some more recent research. 2020, I think this came out, from Zurich, the people who did Barrelfish. And this is targeting kind of these highly heterogeneous system on chips. And the goal is to be able to manage the memory across, or the memory access across all of these processors. Because currently most operating systems like Linux and so on really focus only on those application processors and rely on other things like device drivers or proprietary code or other code running on those processors to control memory accesses by all of those other processors. So manage the memory access of all the processors, and manage the different sets of the physical memory that are around in a system, right? It's no longer true that we just have processors and one chunk of RAM that the processors access. There's a whole bunch of different memory address spaces all over the place. These can be, device registers. These can be DMA-able memory. These can be memory associated with other processors. Other accelerators and stuff like that can have their own memory and stuff. And so we need a way to holistically kind of manage all of that memory in a system. And so the approach that they propose is to have a model of all the address spaces on a system and their relations. So the relationships between them. So what are all the address spaces? And then have an explicit access control for the memory mapping. So explicitly say what kind of mappings are allowed. So if you've got a device that's running like a DSP or a GPU or something, which memory is it allowed to actually access of the main RAM, for example, right? So you want to explicitly state that. So you want to, know what all the address spaces are, and then have an explicit model of what mappings of those various address spaces are actually allowed. So before I talk a little bit more detail about that, I want to talk about what kind of problems this is trying to address. So this is an example of a Qualcomm chipset. So it's got kind of your Linux application processor running there. It's got system address space with its RAM here. The MMU protects access to the RAM. So different processors on the application processor can access different RAMs. The kernel can rack different memory. The kernel can access all the memory and so on. But then you've also got this kind of DSP that's running the wireless chipset, right? So it's running the Wi-Fi and the modem and so on. And it's actually its own processor. It's got its own kind of MMU and access to memory. And its access to the system address space is protected by the system MMU. And so the system MMU does a similar thing as the MMU. It maps kind of these physical addresses into virtual addresses that the communications processor sees and prevents it from accessing memory that it shouldn't have access to. And the SMMU is programmed by the application processor. Then there's the actual registers for controlling the DSP is also part of the address space and so on. So not too long ago, there was a security vulnerability in this Qualcomm chipset, or in a whole bunch of the Qualcomm chipsets called Qualpone. It consists of a bunch of different attacks, but the first part of the attack was an over-air attack onto the DSP, onto the software running on the radio, on the modem, that could execute code on there, which is bad enough, but it's a separate processor, and in theory, it can't affect what's running on the application processor, which is your phone, right? Your Android. And so, in theory, this SMMU protects it from doing anything bad. But what they discovered was that the way it normally works is there's a Linux driver running on the application core for this modem, and it basically tells the DSP, because it needs to do DMA and so on, it says use this address for DMA, right? I've allocated some buffers. I'm going to use these for DMA, so these are the addresses you're going to use for DMA, but they're in Linux's address space. And so the DSP needs to take that, it needs to take those addresses, it needs to figure out its local mappings for those, and then it communicates back to the driver and says, okay, these are the mappings I need you to make in the SMMU for me so that I can actually access this, because otherwise it can't access the memory to share. And so the Linux driver says, okay, it's in the kernel, so it programs the SMMU to allow those accesses. And that's how it normally works. But once the DSP was compromised, what it did was it told the Linux driver, and it said, hey, why don't you just map the whole address space for me of the kernel? And so it said, okay, sounds good to me. And so it did that. And so now, like, this software could access any memory of the kernel, and it could, cause its own code to be executed and could compromise the Android running on there. And so the problem here is that the kernel doesn't have kind of this holistic view of what the DSP should be allowed to access. It should definitely not be allowed to access the whole address space. But it trusts the driver to give it access to the address space. And so it trusts the driver to understand what it should and shouldn't be able to access. And if that driver doesn't realize that it could be compromised and ask for the wrong thing, it'll give it the wrong thing. But there's no kind of centralized way of managing that memory, right? So there's all these different pieces of memory, different people, different processes that want to use that memory, but there's no central way of managing that. And so this work on MMAP-X is about providing this kind of access control to all the various heterogeneous pieces of memory and hardware on a system. And so it's essentially split into two parts. There's a policy part. There's a way of specifying, again, what are all the address spaces that are available, but what's allowed in terms of mappings. So if we go back to kind of the Qualcomm example, mapping the whole address space to the DSP is not allowed. And so the policy should forbid that from happening. Right? The policy shouldn't allow that from happening. So they use this thing called a decoding net, which is a formal way of representing all of these mappings, all the allowed mappings. And then there's a mechanism part to it, which is a reference monitor. Right? If you recall, a reference monitor is a piece of software or hardware where all references all attempts to perform some operations go through the reference monitor, and it checks whether they're allowed or not. And if they are, it allows that to happen. If they're not, it rejects them. And so in this case, the reference monitor needs to make sure that any mappings that are attempted are allowed by the policy. So all mappings have to go through the reference monitor. Now in this case, the reference monitor consists of two things. It consists of all the translation hardware in the system, so the MMU, the IO MMUs, the system MMUs, etc., and then the OS kernel. So all address space mappings go through the OS kernel. The OS kernel checks with the policy whether a mapping is allowed or not. And if it's allowed, then it'll configure the translation hardware accordingly to make that mapping happen. So it might set up the MMU, it might set up the SMMU, etc. accordingly. And that way it ensures that the system can only perform and create mappings that are allowed by the policy. So they implemented this in Barrelfish using capabilities. So basically, they had a policy database, and the policy database contained a representation of the hardware and all the address spaces in there and what kind of mappings were allowed. And that led to a set of capabilities. And then if you want to do any kind of mapping, well, it's the usual kind of capability-based approach. So you used to from SEL4, if you want to map a page into a page table, then you need to have a capability for the page, you need to have an appropriate capability for the page table, and you do the mapping. Likewise here, right? If you want to map a page into the SMU for the DSP device, then you need to have the capability for that page, you need to have the capability for the SMMU, and you need to map them accordingly. If you don't have a capability for that page, you can't map it. So if the DSP asks you to map the whole address space, but you only have capability for a particular buffer, well, you're only going to be allowed to map that capability. You can't map the whole address space. And so it protects you from those kind of attacks. They have a conceptual model for how you can do this in Linux as well. The idea being that there's a system call, rather than mmap, it's mmapx, where you specify a source address space and a destination address space. So you're saying, I want to map some chunk of a source address space, that could be your physical address space, into a destination address space. That might be your process's virtual address space. So you ask the kernel to do that, and it either allows it or not. In this case, they have file descriptors which act as your capabilities, and then they have a file system dev.as which represents all the various address spaces, and they use kind of Linux access control to manage access to those address spaces. So if you have access to the address space, then you can do mappings. But if you don't have access to the address space, then you can't do the mappings. So yeah, so that's kind of a cool way of doing this kind of thing in Linux. You essentially using file descriptors as capabilities, for example. So they've implemented that, and that actually works really well. They show that they can do a lot of really complex address space, a lot of really complex kind of hardware structures. They can represent that there. They can do the protection accordingly, and it doesn't provide significant overhead at all to do that. So that's a really cool way of how to deal with some of the heterogeneity in the systems. All right, so that brings us to an end. I'll just end with a bit of summary of kind of what we've seen. So we've looked at kind of trends in multi-core where scale is getting big. We've got newer machines, potentially no cache coherence. Really our computers are distributed systems, and there's more and more heterogeneity coming on. We've looked at kind of general guidelines for how to design OSs for that. Avoid shared data, do explicit communication, and ensure locality. And then we've looked at specific kind of design approaches to doing that. So partitioning the machine, reducing sharing, no sharing, and how to deal with heterogeneity. So that's all for multi-core OSs. I hope you go out and build some awesome OSs. And thank you.